Testing 1 2 3. Testing 1 2 3. Alright, so we're going to continue with chapter 9.1 and you to look at chapter 9.1. We are talking about crude as a source of hydrocarbons. So as you can see here, this particular slide is on crude oil, so you need to turn to page 192. This fossil fuels such as coal, oil, and natural gas come from the remains of plants and animals. When prehistoric marine microorganisms such as bacteria and plankton died and were buried by sands millions of years ago, these organisms accumulated as organic sediments and gradually became part of Earth's crust. There millions of years, this organic material was affected by high temperatures and pressures, causing the oils and fats to be converted into hydrocarbons. So this mixture of hydrocarbons is crude oil. So in general, when we are talking about crude oil, we are talking about the petroleum that is coming from the ocean or from the ground. And this petroleum in the form of hydrocarbon has been around for millions of years, and because they are under high pressure and temperature, eventually the oils and fats will be converted into hydrocarbons. And later on, when we are talking about hydrocarbon, it consists of carbon, so C represents carbon and hydrogen, as what we have previously discussed in class. So if you're talking about combination of carbon and hydrogen, we are referring to that too as a hydrocarbon. So moving on to the next slide. So it says here crude oil has a low density, which means that it could migrate upwards through the crust, where it often became trapped beneath impervious, unable to pass through rock. Accumulation of oil and gas under rock creates an oil field. So if you look at this particular diagram here, it's a typical structure of the impervious rock that traps oil and natural gas underground and creates an oil field. So if oil and natural gas being trapped underground for a long period of time, you're talking about millions of years under high pressure and temperature, eventually they will be trapped and they will be turned into hydrocarbons in this particular scenario. Move to the next slide. So this is of the fractional distillations of crude oil. As you're probably aware, the petrol that you use at the fuel pump, or the fuel that you use at the fuel pump at the petrol stations, it is just a very small component of the original crude oil that is being present in the ocean or from the ground. So it is crude oil is not used in raw state. It's transferred from oil fields to oil refineries, where it undergoes fractional distillation in a fractionating tower. So in this process, the crude oil is separated into various components or fractions. Each fraction is made up of a range of hydrocarbons with similar boiling point and hence molecular masses. The components of crude oil that are obtained by fractional distillation are used by a wide range of purposes, but presently over 90% of them are used for fuels. So if you look at this particular diagram here, you can see that it is being separated through a difference or change in boiling point. We may have gone through this in the last few chapters when we talk about fractional distillations of crude oil. So in this case, the lower the boiling point, the higher that it will rise in that fractional distillation chamber. Whereas those that have a boiling at a very high boiling point will sink to the bottom of that fractional distillation chamber. So usually there is a correlation between the length of the carbon chain as compared to a boiling point. The longer the length of the carbon chain, the higher the boiling point. So you can see at the bottom, it has the longest carbon chain as compared to, let's just say, if the carbon chain consists of 1 to 4 carbons, the boiling point range will be less than 40 degrees Celsius. So you can see that they have different applications for the different components of the crude oil. So let's just say that if you're talking about if the chain is a very short chain, it will be used for gas fuels, for cooking and for heating home. If you're looking at those that are of very long chain, they are unvaporized residues. They are used for as spuds and tars for roofing and paving. So those root tar is made of the unvaporized residues that has very long carbon chain, which means that they will have a very high boiling point as compared to the petroleum gas that you use at home for cooking. Moving on to the next slide. So cracking of hydrocarbons is heavier fractions undergo a process called cracking. This process breaks the larger hydrocarbon molecules into smaller molecules using heat and a catalyst. You see, the smaller molecules, especially those with carbon-carbon double bonds, are needed by the petrochemical industry. So for example, if you look at this particular chain here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbon chain molecule, as you can see here. If it undergoes cracking, it results in two smaller molecules, and one of which will have carbon-carbon double bond, as you can see here. We discuss single and double bond later on, but in general, double bond means that two valence electron is being shared by each of the atom. If it's single bond, it's just one valence electron is being shared by each of the atom. So what cracking of hydrocarbon means is that you're breaking up the long hydrocarbon chain into shorter hydrocarbon chain. Move on to the next slide. So alkanes, these hydrocarbons are composed only of carbon and hydrogen. As mentioned before, when we are talking about hydrocarbon, they only consist of carbon and hydrogen. Is it the simplest hydrocarbon is methane? We talk about methane when we are talking about the covalent molecule. Still remember the formula of methane is CH4, which means with one carbon being bonded to 4 hydrogen atoms. It said methane is the first of a series of compounds known as the alkane. Alkanes are hydrocarbons that contain only single bonds. All the carbon-carbon bonds in alkane are single covalent bond. Molecules such as these are known as saturated. Saturated means that they do not have double bond. If the particular molecule consists of double bond, which means that it is known as unsaturated. So when we are talking about alkane, they are saturated. They consist of only single bond. A very good example here would be methane, and we know that methane has a formula of CH4 and it has the tetrahedral shape. The bond angle is 109.5. So that is the formula of methane, CH4. Moving on to the next slide. Alright, so as mentioned before, when we are talking about alkane, you are talking about it having single bonds, in which it is a saturated hydrocarbon. It is a saturated hydrocarbon. So in this case, when we are talking about alkane, it says here the series differs from the previous member by CH2 unit. It's a stereochemical molecule in which each member differs by CH2 from the previous member is known as the homologous series. These compounds that are members of the same homologous series have a similar structure, a pattern to their physical properties, similar chemical properties, the same general formula. So these are the criteria that we have for compounds to be members of the same homologous series, which means that if you are comparing the alkane structure, they should have a very similar, or they should have the same chemical formula, but what differs is the number of carbon. That is something that you must be very clear, which means if you come across a molecule that has a double bond, it cannot be an alkane structure or an alkane molecule, because alkane molecule only consists of single bond. If it consists of double bond, it is not an alkane molecule. Moving on to the next slide. Alright, so now we're looking at properties of alkanes. You see alkanes are non-polar molecules. As a result, they are insoluble in water, and the only attractive force between the molecules is dispersion. Why it only have dispersion forces? Going back to what we have discussed when we're talking about intermolecular bonding, bear in mind, alkane structures are non-polar. How do we know? If you look at this diagram on the right hand side of the slide, methane CH4, ethane C2H6, propane C3H8, it only consists of carbon and hydrogen. In a way, it is symmetrical. If you look at the methane structure, it's symmetrical, ethane is symmetrical, propane is symmetrical, even though there is a difference in electronegativity between the hydrogen and carbon, but because they are all symmetrical structures, all of them are non-polar as a result. But what you can see, if the molecular size increases, you can see that the boiling point increases as well. As you can see, methane has a boiling point of minus 164, ethane is minus 87, propane is minus 42. You can see that boiling point increases when the structure increases in size. So methane is used for cooking, Bunsen burner, gas heating. Ethane is used for conversion to ethane, and propane is used for liquid petroleum gas. We'll talk about ethane later on, but you're probably aware by now, for an alkane structure, all that ends with A and E, and the larger the molecular size, because of the increasing dispersion forces, bear in mind they are non-polar molecules, because of increasing dispersion forces, the melting and boiling point of the alkane structure increases as well. But they are all non-polar molecules, which means that they cannot have other forms of intermolecular forces. The only intermolecular force that they can have is dispersion forces. Moving on to the next slide. Alright, so naming of alkanes. Alkanes are named by adding ane after the stem name. For example, an alkane that contains a carbon atom is called alkane. It says the molecular formula of alkane is CaH18. CaH18 is based on the general formula CnH2n plus 2, which means that if the number of carbon is 1, the number of hydrogen will be 2 times 1 plus 2, which is 4, so CH4. If it's 2 carbon, it will be C2H. 2 times 2 plus 2 is 6. So you can get the general idea of it. If you look at every single alkane structure, the only difference is the number of carbon, but the general formula is the same, which is CnH2n plus 2. You see, if an alkane molecule has 12 carbon atoms, the number of hydrogen atoms is 2n plus 2, which is 2 times 12 plus 2, which is 26. So you have a molecule formula C12H26. There's something you need to think about. If the number of carbon is 1, it is known as methane. So I'll highlight this on the right hand side. If it's 2 carbon, it's ethane. If it's 3 carbon, it's propane. If it's 4 carbon, it's butane. If it's 5 carbon, it's pentane. If it's 6 carbon, it's hexane. If it's 7 carbon, it's heptane. If it's 8 carbon, it's alkane. If it's 9 carbon, it's nonane. If it's 10 carbon, it's decane. So you can probably guess. Let's just say that if the number of carbon is 10, so we're looking at the decane structure. If the number of carbon is 10, which is what I'm writing right now on the screen, we know that the number of hydrogen will be 2 times 10. 2 times 10 plus 2. So what do you think is the number? 2 times 10 is 20 plus 2 is 22, which means that your decane structure, which consists of 10 carbon, will be made up of 10 carbon and 22 hydrogen. So 22 hydrogen. So the formula that we use once again is CnH2n plus 2, which means that if you have 10 carbon, the number of hydrogen will be 2 times 10 plus 2, which is 22. Thank you very much. I will move on to the next slide. So this is the final slide that we have, and this is the end of part 1. In the next lesson, when we go to part 2, we will look at how do we write the formulas and how do we name different alkane structures. So there's something that we're going to do in the part 2 of this particular topic. So going to reactions of alkanes, these alkanes generally are unreactive. They are hydrocarbons. Although like most hydrocarbons, they can be used as a fuel. It says the reaction between a fuel and oxygen is known as combustion, which means that if you burn alkane with the presence of oxygen, you release carbon dioxide and water. It says burning of petrol in car engine and the use of nitric gas for cooking, example combustion reaction. The supply of oxygen is plentiful. It says product of combustion will be carbon dioxide and water. So this is known as a complete combustion. Complete combustion means every single of the carbon is being burned with oxygen, it will produce carbon dioxide and water. If it's an incomplete combustion, most likely it will only produce carbon or carbon monoxide. You will not get carbon dioxide, because in order for you to get carbon dioxide and water, you need to have the complete combustion, which means every single of the methane structure has to be burned with the presence of oxygen for you to produce carbon dioxide and water. And this is a balanced equation. I'll be guiding you through on how to write a balanced equation. For now, you know that for methane, the formula of methane is CH4, which is a gas. With the presence of oxygen, it will produce carbon dioxide and water. You have 2 oxygen and you have 2 water molecules, because in order for it to be balanced, you need to have the same number of carbon, hydrogen, and oxygen on both sides of the equation. In this case, the formula will be CH4 plus 2O2. You will produce CO2 plus H2O. So this is the reaction of alkane, and this is known as the complete combustion of methane with the presence of oxygen to produce carbon dioxide and water. So this is done. Ask me questions on social stream. Very welcome to discuss questions on social stream, and you can email me any questions that you have. For now, I'll see you back in class, and then after the end of part 1, in the next lesson, we will continue with part 2. We will look at the naming of different alkane structures and also the drawing of alkane structures as well. So I'll see you then.